In this video, we will solve problems based on rotational equilibrium. Let's look at the first problem. A piece of hanging art consists of two diamond-shaped objects hung from long uniform rod of mass m0. So this rod has a mass of m0 and length L0 as shown in the figure. The diamond shapes have masses m0 and 3m0. The rod is suspended from a vertical cord located at a distance L0/4 from its left end. So the whole thing is suspended with this string, which is at a distance of L0/4 from the left end. The larger diamond shape is suspended from the left end of the rod. The smaller diamond shape has mass m0 and is to be placed at a location such that the diamond rod system will be in rotational equilibrium. So once you suspend the smaller diamond shape, the whole rod is in rotational equilibrium. If the smaller diamond's location is a distance x to the right of the rod's center, so this is rod's center, this point is the center of the rod, and then it's asking which of the following equations is appropriate for determining x. So the first thing which we'll do is, from rod's center we need to show the mass or the weight of the rod itself, which is m0, which will be acting vertically downwards. So we can write this as m0g, and this will be 3m0g, and this will be m0g. The reason is that the force which is responsible for rotating the rod, that's what we want to check. So I'm writing each m0, that is each mass, and multiplying that with g to get the weight. Now the axis of rotation is this. This is your axis of rotation, or this is your pivot. And about this pivot, we need to write an equation for equilibrium. And we know that if it's in equilibrium, tau net and force net will be equal to 0. So let's write down sigma tau equal 0. That means the clockwise moment and counterclockwise moment together should be equal to 0 if we add them up together. Now 3m0 is going to rotate in this direction, which is counterclockwise, and m0 is going to, the rod's mass or the rod's weight itself is going to rotate this way, and the diamond m0 will also rotate this way, which both of them are clockwise. Okay. Now we need to add up the clockwise moment and equate it to counterclockwise moment. So let's find out what is counterclockwise moment. So we know that the formula for torque is Fr sin theta or Rf sin theta, because here the angle is 90, so we can just write it as Rf. So the distance of 3m0g from the pivot is L0/4. So 3m0g multiplied by L0/4, which let's just write it as 3/4 m0 L0g. I've just rearranged it, rearranged the numbers and the alphabets. And now for the clockwise moment, we have got two of them. So first let's write for this. It's at a distance of L0/4. So m0g multiplied by L0/4 plus, we have one more. This one is at a distance of L04 plus x. So m0g L04 plus x. Now we know that clockwise and counterclockwise movement together should be equal to 0. So we can write torque CCW, that is counterclockwise movement, minus torque CW equal 0. Now why minus? Because one is clockwise and so two of the moments are clockwise and one moment or one torque is counterclockwise. So their signs will be different. So if I'm taking counterclockwise as positive, then clockwise torque will be negative. So let's write that 3 over 4 m0 L0g, that's this. Then minus, let's start a bracket, m0 L0g over 4, that's this one, plus m0 g bracket L04 plus x bracket close equal 0. Now we'll just open the bracket, minus m0 L0g over 4 minus m0 g L04 plus x equal 0. Now if we compare, we can see the last one matches with our equation 3 m0 g L04 L0 over 4, which is here, then m0 g L0 over 4, which is here with minus sign, and then again minus sign because we had a bracket here, so the minus will be with both the expressions. So m0 g L0 over 4 plus x, which we can see here. So our answer here is D. Let's look at the next one. A thin rod of negligible mass has a sphere of different masses, attached to its ends. So now here the rod itself is not having any mass, but it has some masses which are attached to its ends. The rod is free to rotate about its axis perpendicular to the plane of the figure, and located at a triangular fulcrum. Fulcrum is pivot that supports the rod. If the rod is held in place horizontally and then released from rest, what is the magnitude of angular acceleration of the rod sphere system immediately after the rod is released? So here the question is slightly different. Here the system is not in equilibrium, because when you release it, we can see that it says it's asking us to get the magnitude of angular acceleration. When you release the system, what's the magnitude of angular acceleration? So we want to find what is alpha. So sigma tau over I for the system, that is net torque over the rotational inertia of the system, will give us the acceleration, angular acceleration of the system. So now to get sigma tau, I'm going to again show the forces which are acting, and then again we'll see which one is clockwise, which one is counterclockwise. So 2m0g is going to rotate counterclockwise, and m0g is going to rotate clockwise. So alpha of the system should be equal to torque counterclockwise minus torque clockwise over I for the system. So let's just calculate each one of them. So torque counterclockwise, torque is, the formula for torque is Rf. Again, the angle here between R and F is 90, so we don't have to write sine 90, so we'll just write Rf. So 2m0g is at a distance of d from the pivot, so we'll write that. So 2m0gd, and clockwise torque will be m0g multiplied by the distance from the pivot is 3d0, so 3, this is also d0, 3d0, so that is 3m0g d0. Now the net torque will be counterclockwise minus clockwise, so 2m0 gt minus 3m0 gd0. Okay, I can take it the other way around also. I can see that this is going to come in negative, and I am interested only in the magnitude, so I can take it the other way around also, that is clockwise minus counterclockwise. But let's just write this, net torque is equal to, So we have got 2 minus 3, which is going to give us -1. So minus m0 g d0. That's our net torque. And the rotational inertia of the system. Now there are two masses, and we need to recall that rotational inertia for point masses which are having some distance from the axis of rotation can be calculated using this formula, sigma m r square. So there are two masses, so we'll write 2m0. So for 2m0 the distance is d0 square plus m0, the distance is 3d0 square. So that will be 2m0 d0 square plus 3 square is 9. So 9m0 d0 square. 9 plus 2 gives us 11 m0 d0 square. Now alpha for system, that's what we want to calculate, which will be equal to the net torque, which is minus m0 g d0, which we are going to write as positive because we want to find only the magnitude. So m0 g d0, let's just move this aside, over the moment of inertia, which is 11 m0 d0 square. So we can cancel out m0. Let's just cancel out what's common. m0 can be cancelled out and one of the d0s can be cancelled out. So alpha system will be equal to g over 11 d0, and that is option E. Now let's look at one more problem on this topic, which is rotational equilibrium. A uniform rod of length L0 is free to rotate about an axis through its left end and perpendicular to the horizontal plane of the figure shown. When a force with magnitude F0 is exerted perpendicular to the rod at the right end, the angular acceleration is alpha 1. So for the first diagram, it's alpha 1. The same force is then exerted on the right end of the second uniform rod with same linear mass density and twice the length of the original rod, as shown on the right side of the figure. The rod of length 2L0 has an angular acceleration of alpha 2. What is the ratio of alpha 2 to alpha 1? So again, alpha is sigma torque over rotational inertia, which is I. And we know that torque, because there is only one force here, we can write that just as Rf. That will be, so let's just write that once again. Each of the system is having only one force, and the moment of inertia will be, or the rotational inertia is only for the rod itself. There is no other mass which is hanging or which is attached. There is no other mass attached to the rod. This is the axis of rotation, or this is the pivot. So for the first system, the pivot is here. For the second system, the pivot is here. Okay, so we can write alpha as Rf over mr square. So torque, we remember that we can recall that torque is Rf and I is mr square. I'm not writing sigma because there is only one mass in each of the systems. So if we see this R gets cancelled out, so if I want to find alpha, it will be F over mr. Now we are going to find alpha 2 over alpha 1. So we'll write F2 over m2 R2, okay, divided by, so that's our alpha 1 using this formula, and then division divided by F1 over M1 R1. Let's rearrange that. F2 over M2 R2. Multiplication, division gets converted to multiplication, and then we take the reciprocal of the second expression. So M1 R1 over F1. But we can see that the forces in each one of them is same. That means these both forces are equal to F0. They get cancelled out. So we can just cancel out these two forces. And so, because it says same linear mass density, so linear mass density means same mass per unit length. So it's saying that the mass per unit length is same for both of them, but we can see that the second rod is twice the length. That means the mass of second rod will be 2 times the mass of first rod. So we can write that M2 is equal to 2 M1. So let's write that. And also let's check R1 and R2. So what is R1 and R2? That's the distance from the axis of rotation. So for each one, we'll draw where is the center of mass of the rod. So here it will be in the center of the rod. This is where the mass of the rod is acting. Okay, and the distance is L0 over 2. And for this one, this is the point where the mass of the rod, or the weight of the rod, not the mass of the rod, weight of the rod is acting, and the distance here is half of L0, sorry, half of 2L0, which will be L0. So here it is half of L0, and here it is half of 2L0, which will be L0. So that means here R1 is equal to L0 over 2, and R2 is equal to just L0. Now we will substitute these things in our equation. So this was M1 R1 over M2 R2. I'm just copying it as it is from this equation. Then M1, we can use this equation. So I'm just keeping M1 as it is. R1 is L0 over 2. M2 I'm going to substitute as 2M1, and R2 is L0. So what I did here is this M2 I have substituted using this equation 2M1. R2 I have written as L0 from here, and R1 I've written L0 over 2 from here. So now we can see M1 can be cancelled out from the numerator and denominator. L0 can also be cancelled out. So we have got 1 over 2 over 2, which we can write as alpha 2 over alpha 1 will be equal to 1 over 4. So this 2 will go here and get multiplied. That will be 1 over 4. So our correct option is 1:4.